In this video, I'm going to talk about sampling distribution of mean or distribution of sample mean. What does that mean? Okay, let us see an example. Suppose that the average age of COVID-19 patients is 71 years and standard deviation is 11 years. Suppose that they collected all the data, everybody who were infected by the COVID-19, and then they recorded the age of all the patients. Okay, that means the population mean is 71 years because this is the average of all the COVID patients. Okay, and the standard deviation is 11 years. Okay, now why do we need statistics? Statistics is needed to work on the samples, because statistics work on the sample, meaning it may be harder to collect all the data of the COVID patients around the world. Okay, so what you want to do is you want to select sample of people from different parts of the world and find the mean of those samples and find the mean of those means. And then you can say that if you find the mean of the means is 72 years, then you can estimate the population. You can say that from the sample means we found that the mean is about 72 years. Then you can generalize that result to the whole population. Okay, so that's what the statistics do. Statistics work on the sample, and whatever result you find out from the sample, you apply that result to the whole population. Okay, now the population mean of the population average of the age of the COVID-19 patient, let us suppose that is 71 years and the standard deviation is 11 years. Now what I want to do is I want to find out the population mean. I want to estimate the population mean from the sample mean. What I want to do is I want to pick many samples. Okay, sample of size 35. I will take one sample of size 35, let's say from eastern part of the United States, and then find the sample mean. Let's suppose that I found one sample mean as 70, meaning the average age of those 35 people that I picked each sample of 35 people, 35 patients, and then from one sample I took from the eastern US, I found this average is 70 years. Let's say I want to take from south. Okay, I suppose that I found that 73 years. Okay, from north, let's say I found it is again 70 years. From west coast, let's say I found it is 72 years, and then so on. Meaning I am picking many samples. Actually I am picking 200 samples. Okay, and then each sample has size 35. That's what I'm doing here. Okay, after you collect all the means, after you calculate all the means of each sample, now I want to write in a table. Okay, suppose there were 5 samples with mean 66. Let us say there were 8 samples with mean age, the average age 67. There were, let's say, 10 samples with age 68. Okay, and let us suppose that the average age, let us suppose that there were 15 samples with mean average 69. Okay, similarly there were 20 samples, let's say, or you can say 30 samples with mean 70. Okay, and then 71, there were, let's say, 50 samples. Okay, 72, let's say there were let's say 35 samples with average age 72. There were, let's say, 27 samples with average age 73. Let us say there were 10 samples with average age 74. There were 7 samples with average age 75, and there were 3 samples with average age 76. This is just an example. Okay, these numbers may be different in the real situation, but this is just an example. So what we did is, in the whole population, suppose that the average age of the COVID-19 patient is 71 years and the standard deviation is 11 years. Okay, now what we want to do is we want to check that. We want to do that study again. We want to know what is the average age of the COVID-19 patients by taking different samples. Okay, what we want to do is I want to collect 200 different samples with each sample size 35. Suppose the first sample has average age 70 years. The second sample has average age 73 years. The third sample has average age 70 years. Fourth sample has average age 72 years. And then so on, continue that way. 99th sample has average age 70 years. 100th sample has average age 60 years. Because each of these samples have sample size 35. We are picking 35 people and then find the average age of those 35 people. Okay, and similarly you continue, and then now there are 200 data points here, right? 200 sample means, right? What I want to do is I want to make a table with mean and frequency. What does that mean? Suppose there were 5 samples with mean 66, because see, you see the 70 is repeated, similarly the 66 is repeated, 67 is repeated, and so on. So what I'm doing is I'm making the table for these findings. Okay, there were 8 samples of average age 67, 10 samples average age 68, 15 sample of average age 69, average age 30, 70, average age 70, 30 samples. So the total here is, let's say, that is 200. Okay, now I want to find out the mean of those means. How do I find out the mean of the means? What you do is you want to find out f times x, right? And then multiply these two and write down there, multiply these two, write down there, multiply these two, write down there, and so on. Okay, and then suppose that let me show you actually how do I use calculator to find out the mean in the in calculator. Okay, so what you do is, this is like x. Okay, basically it is x bar. I mean, you can write this as x bar, and then this is like f, right? So f times x bar is here. So what I want to do here is I want to find out the mean using calculator. I want to use calculator to find out the mean of these data points. To do that, what you do is go to stat and then hit edit, hit enter. So there are already data. So what I want to do is I want to clear those data. Okay, so let me clear that, hit enter, and I want to clear L2 as well. Go up and then clear it. Okay, now what I want to do here is enter that 66, 67, and so on. 66, 67. Similarly, I want to enter the frequencies in L2, 5, 8. So after you enter the data and the frequency, what you do is go to the stat and then calc. Okay, one variable status. So the list, the x values are in, x bar values are in L1, the frequencies are in L2, and then you hit calculate. This is what you get. See, the x bar is 70.965, right? Basically, x bar. So the mean of the means, right? So usually people write like mu x bar, right? That is 70.9, which is almost 71 years, right? And then what was sx is 1.x was 1.91, right? That is, we write s x bar because this is the standard deviation of the x bars, right? That is 1.91. That's what we found. Okay, now let us see here. So what we did so far is we knew that the average age of the COVID-19 of the population is 71 years and the standard deviation is 11 years. Okay, so mu is 71, standard deviation is 11 years. Okay, now, so we want to check. Okay, so what we want to do is we want to find the different samples with the same size, 35, and record the mean age, average age of each of the sample, and then we made the table and then noted that we just basically rewrite those in the tabular form. There were 5 samples with mean 66, 8 samples with mean 67, and then so on. So the total there were 200 samples. Okay, now what we did here is we used calculator to find out the mean of those sample means. Okay, and then also standard deviation of the sample mean. Did you notice that the mean of the sample mean and the population mean are the same, right? You see that the mean of the sample mean and the population mean, they are the same thing. We got the same number. Okay, but the standard deviation of the sample means, the standard deviation of the sample means is smaller than the standard deviation of the population. You see, the whole population has bigger standard deviation than the then the standard deviation of the sample means. Okay, so let us note that down. Mean of the sample. So this table, this distribution is called sampling distribution of the mean, because one of the column is sample mean, the other column is the frequency. Okay, now this is called sampling distribution of mean, or distribution of sample mean. This is called distribution of the sample mean. Okay, now what we found from here is mean of the sampling distribution is equal to the population mean. That's what we found, because that value and those values are almost the same, right? So the mean of the sampling distribution is equal to the population mean, but the standard deviation of the sampling distribution, the standard deviation of this sampling distribution is smaller than the population standard deviation. That's what we got, because this is 1.91, this is 11 years, right? It is given by how much small is it? Is sigma over root n. What is sigma? Sigma is that 11, right? So 11 over root under n is how much? N is the sample size, right? Sample size is 35. How much is that? That is 1.86. Almost equals to 1.9, right? So 1.86, which is almost equals to 1.9. You see that? You see that? What it says is, if you collect the sample of the same size, many samples of the same size, and if you find out the mean of each of those samples, and if you find out the mean of those means, okay, then that mean of the means is equal to the population mean. And if you find out the standard deviation of those means, that will be smaller than the population standard deviation. So how much small is that? That will be the population standard deviation divided by root under the sample size, will be almost equal to the sample mean. So sample mean is basically Sx bar is almost equal to that value, 11 over root under n, or the sigma over root under n. That's what it says. Okay, in other words, we can say that, let me do one more thing on here. Okay, let us draw the histogram for this. Okay, if you want to draw the histogram, how would that look like? So there will be, like, let us say this is the maximum one is 50, right? So suppose this is 50, so 40, 30, 20, 10. Okay, so if you draw the histogram, so 66, there is 66, 67, 68, and 70, 71, 72, 73, 74, 75, 76. Okay, if you draw the histogram for each of those, so the first one is 5, and then other one is 8. First one is 5, the other one is 8, right? Let me erase that. If you draw the histogram, this is what you will see, and then you will see the shape of the distribution, right? So another one will be 10. 10 is also almost, I mean, this is not perfect, but it is just the estimation of how that look like, right? And then another one is 15, and then 30, right? And then 50. The 50 is somewhere here. And then if you do that, so you will get something similar to this. So if you draw the graph of this, you feel like a bell shaped. Okay, so this is almost normally distributed. Okay, so what we see here is the sampling distribution of mean is approximately normally distributed. Okay, you see that the sampling distribution of the mean is approximately normal. But when? Because the sample size is bigger than 30 here. Okay, so the sample size here is 35. Okay, and the sampling distribution of the mean is approximately normal. The mean of those means is equal to the population mean. The standard deviation of these means, sample means, is almost equals to the population standard deviation divided by root under the sample size. Okay, this is what we found, and this is what it says. So x bar, meaning the distribution of the x bar is approximately normal, with mean is equal to the mean, but the sigma is equal to the sigma over root under n, or the standard deviation of the sample means is equals to sigma over root n. That's what this example tells you. Okay, all right. So the next thing we will do is the central limit theorem. That's what it says. Central limit theorem says that If you pick the sample size sufficiently large, then the distribution of the sample mean is approximately normally distributed. Instead of taking a sample size 35, if you take a sample size, let's say 5, then you may not get that result. Okay, you may not get that result. You may get different result. So what it says is, if the sample size is big enough, then the distribution of the sample mean is approximately normal. Or in other words, if you increase the sample size, then the distribution of the sample mean will be approximately normal, and that distribution has mean is same as the population mean, and the standard deviation will be same as the population standard deviation divided by root under n.